In this video, we will cover the reactions of esters and amides. So we're going to do an esterification and an amidation reaction. And the reason I'm lumping these together into the same category is because they behave very similarly. So in either case, they're going to produce a water molecule. And the only difference will be in the fact that in esterification, we're reacting an alcohol with a carboxylic acid, whereas in an amidation, we're reacting an amine with a carboxylic acid. So on the left here, we have a carboxylic acid, which you can identify based on the fact that there is a carbonyl connected to an OH group. And on the right, we have an alcohol. When you see the two of those together, they are going to combine to form an ester in what we call an esterification reaction. So esterification just means they are forming an ester molecule. The first thing I'm going to do is find some way of generating a water molecule. And notice there's an OH on the carboxylic acid, and I can take the hydrogen from the alcohol to form H2O. So this component is going to form a water molecule. And you could have done this in the other direction. So alternatively, you could have taken the OH from the alcohol and the hydrogen from the carboxylic acid. That would also yield the exact same product. So either way that you do it will be fine. Okay, so notice here we can generate a water molecule. So I'm going to remove that as water, and the remainder of this compound, I'm just going to connect to each other. So I'm going to take that carbonyl carbon right here and connect it directly to the carbon from the alcohol. And you're just going to fuse them together into one compound, and that will be the ester. So I'll keep my color coding to be consistent. That's my carbonyl carbon, and there's the carbon from the alcohol. And notice that here we generated an ester. So an ester is going to have the pattern of a carbonyl carbon that is connected to an oxygen, and then to another R group, which can be just any hydrocarbon chain. So that's an ester. So in an esterification, you're producing an ester by releasing a water molecule. Now keep in mind that esterification is a reversible reaction. So you could actually go backwards. We could take the ester product that we had, we could react that with a water molecule, which I'm just going to write as HOH because it will be easier to see where we are breaking it apart. And if you see acid and heat, in both scenarios we had acid and heat. The acid is just serving as a catalyst. So the acid and the heat are just there to make the reaction go faster. You can effectively ignore them when you're doing the reaction. So in the reverse, we're starting with an ester, and we're just going backwards. So we're going to have to produce a carboxylic acid and an alcohol. And when we do the reverse of that reaction, we call this ester hydrolysis. And this ester hydrolysis is happening under acidic conditions because we have acid in solution, which is good for our carboxylic acid because it's also an acid, so those two are not going to react with each other. Okay. I need to produce a carboxylic acid, which means I'm going to break up the water molecule, and I'm going to break a bond right here. So in order for this part of the molecule to turn into a carboxylic acid, it needs to have an OH group. And I'm going to take the OH from the water molecule. So I'm going to copy those over and connect them to each other, and color code to be consistent. And there is my carboxylic acid. Keep in mind that the other component of forming an ester was an alcohol. So if I'm going backwards, I also need to generate an alcohol molecule. Well, if I take the oxygen and the remainder of that alkyl chain and I give it a hydrogen, I can fuse those together to form an alcohol. And there's our alcohol product. So esterification and ester hydrolysis are just the opposites of each other. They're going in exact opposite direction. Now, the reason I lumped in amidation with this whole process is that it's a very, very similar reaction. The difference here is that we're going to generate an amide, hence the name amidation. And much like the esterification process, we're going to form a water molecule. Now here it's very obvious where the oxygen will come from because the only OH is on the carboxylic acid. And I need to give it another hydrogen to form a water. It doesn't matter which hydrogen you take from the amine. I could take the one up top or I could take a hydrogen on the bottom. They're completely equivalent, so it completely does not matter which one you take. So I will take that one just because it's right next to it. Why not? And that will form a water molecule. And much like we did with esterification, we're going to connect the rest of that structure to the nitrogen. So we're going to fuse those together. So here is a water molecule I produced as a byproduct. And then I will combine the rest of these structures. And there is our amide. So notice we reacted an amine and a carboxylic acid in a very similar way to what we did to form esters. Now, amides are really, really important because these are going to form peptide bonds when you start putting together amino acids to form the primary chain of proteins. So when you're forming a peptide, you're really just taking a bunch of amino acids and forming amide bonds between them. So let's take a look at how that applies to the primary structure of proteins. Here I listed a few amino acids, and I specifically chose small ones with tiny R groups just to make this a little bit easier to draw. So if you recall, the amino acid is classified based on whatever group is up top here. That's what we refer to as the R group, because it could be a variety of different things. The part on the bottom here that I am highlighting right now, notice that that's the same in every single amino acid. So we're not going to use that to classify amino acids because it's very repetitive. So the parts up top are the ones that vary, and that's how we determine which amino acid it is. So the first one is alanine, then we have glycine and cysteine. And we want to form amides to connect these together in a primary peptide chain. And just like with amidation, I'm going to find some way of removing a water molecule. Here's an oxygen, then there's a hydrogen, and I can take another hydrogen next door and combine those to form a water molecule. And I can do the same thing on the following two amino acids. And recall that it doesn't matter which hydrogens you take. I could have taken the one up top and it would be the exact same thing. So that is also going to generate a water molecule. After that, all you are doing is connecting the carbon on that carbonyl structure to the nitrogen. And then you are fusing those structures together to form an amide. So I'm effectively going to copy what we have here. And I'm going to connect it to the remainder of the next structure. And there is my first amide. Now, notice that this nitrogen becomes neutral now because now it has 3 bonds, which is how many bonds a nitrogen wants to have. So it's neutral, it's happy, all is well. That's the other piece of the puzzle. As you connect these into amides, you start to lose these positive charges. And there is my next amide bond. So the bonds that I am highlighting here in blue, those are the amide bonds that we just formed. And peptides are always formed from the N terminus to the C terminus. And those are named based on the atom that is indicated in the structure. So notice how here the chain ends in a carbon, hence C terminus. And here the chain ends in nitrogen, hence N-terminus. So the reactions that form amides also apply to these larger structures. Similarly, the reactions of esters are going to apply to triglycerides because triglycerides have 3 esters within them. So take a look at ester hydrolysis and notice how we are breaking the bond between the oxygen and the carbonyl carbon using water. We can do the exact same reaction on a triglyceride. It's just a larger structure. So here, notice we have 3 ester bonds. And just like with ester hydrolysis under acidic conditions, we have an acid serving as a catalyst and we have heat. The fact that we have H3O+, you can think about it as an H+, so an acidic proton, and a water molecule. So that means there is water in solution here that is going to hydrolyze this molecule. So I'm going to go through and I'm going to break every ester bond. And the reason this is called triglyceride or triacylglycerol is because we have a glycerol as the backbone. So right here, that is a glycerol structure. All it's missing is a hydrogen to turn it into an alcohol. So I'm going to break that structure apart and I'm going to turn this into an alcohol. And in order for it to become an alcohol, it's going to need a hydrogen. There is our glycerol piece of the puzzle. Now we'd like to go back for a moment. Notice when we did ester hydrolysis, when we broke that apart, we generated an alcohol. We just did that with glycerol. The other piece of the puzzle was a carboxylic acid. So if we go back to our triglyceride, we are going to have to take each of these fatty acids. Well, they're not much of a fatty acid right now since their chain is so short, but let's just give them an R at the end. We're going to have to churn every single one of these into a carboxylic acid. And the only piece that they are missing is an OH group. So if you take each of these off of the structure and give it an OH, it turns into a carboxylic acid. So these are going to generate 3 fatty acids. So same reactions that esters do on a smaller scale, they also do when they are in a larger structure. Now, the one more thing that I should mention is that this is done under acidic conditions. And there's one more piece of information that we should talk about, and that is that ester hydrolysis can also be done under basic conditions. So I will copy this over. But I'm going to change the conditions here a bit. I'm going to give it sodium hydroxide and water. So this will be done under basic conditions. Now, the first step of ester hydrolysis under basic conditions will be exactly the same as the hydrolysis that occurs under acidic conditions. However, here we are generating a carboxylic acid, and the name alone tells us that it is an acid. And we are reacting this with a bunch of base in solution. Sodium hydroxide is a very strong base. It comes into contact with an acid. Those are going to neutralize each other. So the second step of this process is a neutralization reaction, where sodium hydroxide reacts with the carboxylic acid. Now, keep in mind that bases are going to accept hydrogen ions, and we can actually rewrite sodium hydroxide as a cation and an anion, since they have an ionic bond. The OH part here is the basic component. So this is the component that's going to accept a hydrogen ion. And it's going to get that hydrogen from the carboxylic acid. So I'm going to take that hydrogen and I'm going to give it to the OH molecule to produce water. and I can just write that as H2O. Now, all that's left is this carboxylate and the sodium ion, and those are going to be in contact with each other. So once we take away that hydrogen, the carboxylate will have a negative charge, and the sodium ion will stabilize it. So these are going to produce an ionic bond, or what we call a salt. Alternatively, you could omit those charges and just write the carboxylate with a sodium next to it, which implies that we are looking at a positive and negative charge